The next type of quadratic trinomial we will encounter is known as the difference of perfect squares, the difference of two squares. This will be a quadratic trinomial that consists of the x squared term and a constant. And the word difference means subtraction. So it must be subtracting in between the two terms. These numbers that you see on the left are called perfect squares. The exponent of 2 means you're multiplying the same number twice. For example, 3 times 3 is 9. We're multiplying 3 by itself 2 times. We can recall that, or we can redefine that as 3 squared. Exponents is a shortcut to multiplying the same number over and over again. Now here's a definition when you're factoring using the difference of two squares. Let p squared and q squared be perfect squares. Thus, if p squared minus q squared is equal to 0, then p minus q times the quantity of p plus q is equal to 0. I don't have a and b here. That should be p and q. Probably a mistake thinking about the alphabets. Let's change it to p and q. Let p and q be perfect squares and subtraction between the terms with the equation equal to 0. Step 2, take the square root of the first term and the second term. Step 3, multiply the sum of the terms and the difference of the terms. Step 4, use the zero product property to find the solutions. So once again, take down this list of perfect squares. They may be on the next slide, which they are, and keep that in the back of your head. Look for these numbers, 1, 4, 9, 16, 25, 36, so on and so forth. Those indicate perfect squares. Now, example 1, find the solutions to the quadratic equation x squared minus 25 equals to 0. Well, there's an invisible 1 in front of x squared. We can put the invisible 1 right here if you want. And we know that 1 is a perfect square because it's right there. So I'm going to erase that, but just remember there's an invisible 1 in front of the x squared. That's good. That number is a perfect square. 25 is also a perfect square as well. 25 is 5 squared. We can factor using the difference of two squares. Let's go back up and follow the steps. Step number 1, make sure that the first term and the second term are perfect squares and subtraction between the terms with the equation equal to 0. Excuse me. Well, we have that. So, step number 2, take the square root of each term. So let's take our x squared. Let's put it over here on the side. Take our 25, put it over here on the side as well. And we're going to take the square root of each term. Now, go back to algebra 1. The square root of x squared, that's just going to be x. The reason why is because there is an invisible 2 on the root. And when the root and the powers are the same, they simplify each other out, leaving us with just x. Now, the square root of 25. What number do you multiply by itself 2 times to get 25? That's going to be 5. And how do we know that? Well, because 5 squared is 25. 5 times 5 is 25. Now, step 3 says multiply the sum of the terms and the difference of the terms. Let's go ahead and do that. Let's multiply the sum of those two terms, so x plus 5, with the difference of the terms, x minus 5, and set it equal to 0. Step number 4, use the zero product property to find the solutions. Now we can utilize the zero product property in succession. by setting both pieces equal to 0 and solving for x. So that's x plus 5 equals to 0. And then we have x minus 5 equals to 0. Solve for x for both of those. For the first one, subtract 5 from both sides. X equals negative 5. For the second one, add 5 to both sides. X equals to positive 5. And if you notice, the solutions are the same, except they have different signs. So my solutions in this case, which I'm going to write above, is negative 5 and positive 5. Same number, different signs. We can call those conjugates, but we'll get more into that later on. Now we're going to do the same thing with the next example. Example 2. We must satisfy the following conditions. First, both terms must be a perfect square, subtracting and equal to 0. Well, 4 is a perfect square, because we see it right here. The v squared is a perfect square because it's a v squared. The 49 is a perfect square. And we're subtracting between those two terms. And it's equal to 0. That is satisfied. Step 2, take the square root of each of those terms. So take your 4v squared, take your 49, and take the square root of both of those terms. The square root of 4 is 2. How do we know that? Because 2 to the second power is 4. Square root is going in reverse. The square root of v squared is just v. Once again, you can look at the example above when I show you how we found that. Vx, same thing, just a different variable. Then for 49, the square root of 49 is 7 because 7 squared is 49, going in reverse. So then step 3 is to take the sum of those terms, 2v plus 7, multiply it with the difference of those two terms, 2v minus 7, and set it equal to 0. Now, to end the steps, you're going to use the zero product property by setting both pieces equal to 0 and solving for v. I'll do it down here. So that's 2v plus 7 equals to 0. I'll do the first one. Subtract 7 from both sides. That's 2v equals to negative 7. And to get v by itself, divide both sides by 2. 2v equals negative 7. Divide both sides by 2. These simplify each other out. V is equal to negative 7/2. That's for the first solution. And then for the second solution, which is 2v minus 7 equals to 0, when you solve for v using the same steps, you get v equals to positive 7/2. Same number, just different signs. And those are our solutions. Two more examples. This one says 81x squared minus 289 equals to 0. Let's check our perfect squares list. 9 squared is 81. 17 squared is 289. We are subtracting between the two terms, and it's equal to 0. So we can factor by using the difference of perfect squares. So we're going to take the square root of each. Now, I'm going to do it here as a shortcut. The square root of 81x squared, and I want to put the parentheses ahead of time. Set it equal to 0. Square root of 81 is 9. Square root of x squared is x squared. Or sorry, is x, excuse me. Now remember, we're going to be taking the square root of the second term. Square root of 289, that is 17. Because 17 squared is 289. So one will have plus 17. The other will have minus 17. And if you don't remember the square roots, you can just plug it into your calculator. For example, if you hit second and then hit x squared, the square root of 289 is 17. And then for second, x squared, square root of 81, that's 9. And then we can then find the solutions by using the zero product property. So for this one, we have 9x plus 17 equals to 0. We're going to subtract 17 from both sides after that because, once again, the goal is to solve for x. 9x equals negative 17. Divide both sides by 9 to get x by itself. The 9s simplify out. X equals to negative 17 over 9. This cannot divide any further, so that is the answer. That is your solution. And once again, as we know, the other one will have the same number except a different sign. The solution to this x will be positive 17 over 9. And there goes our solution set. Negative 17 over 9, positive 17 over 9. There we go. The last example. Let's erase this here. Erase that there. So we have 4v squared plus 49 equal to 0. Okay. 4 is a perfect square because 2 squared is 4. 49 is a perfect square. 7 squared is 49. The issue is the addition here. We are adding here. And remember, this says difference of 2 squares. Difference means to subtract. But this is the opposite of subtracting. This is adding. Because you're adding between perfect squares. You cannot take this approach. In fact, whenever you add between perfect squares, it is infactorable. Infactorable. There is no way you can factor this using real numbers. So this cannot be solved. Cannot be solved in the real world. In Unit 3, you will kind of understand why I said in the real world. So that is it for this video. You guys can practice the difference of perfect squares using 13, 14, 15, and 16 on your worksheet. But remember, the sum of perfect squares is infactorable. All right, guys, I'll catch you in the next one. Take care.